There's a video for AQA Mechanics, Impulse and Momentum, section 3.2, where we're considering oblique impacts of objects on surfaces. Before I go into oblique impacts, just a quick revision of things that you've already met. So firstly, the idea that in direct collisions we assume there are no external forces that are acting, and the momentum then depends on mass and velocity, so momentum is mv. We need to consider the idea of elasticity. Remember, that comes from experimental law, and the idea of restitution, which is a measure of how elastic collisions are, so that we have a restitution or a coefficient of restitution called E, and that can lie between 0 and 1, where if it's 0 the objects will coalesce, and if it's equal to 1 then we have what's called a perfectly elastic collision. This diagram shows what's going on with a direct collision with a fixed object, for example a ball being hit against the wall. This one you've met before, so the coefficient of restitution is the separation speed or speed of separation divided by the speed of approach. So v is the speed that is coming away from the wall and u approaching, then E is equal to v over u. Now in these situations we won't need to apply conservation of momentum. In an oblique collision, then as long as the plane is smooth, then the velocities parallel to, or the speeds parallel to the plane aren't going to change because there's no force acting parallel to the plane. And perpendicular, we can look at the effect of E on the speeds. So we can consider the motion in two parts, one perpendicular to the plane where we have E is equal to v over u, and one which is parallel where the speed will be unchanged. Well, before I go on and look at a numerical example and working out some speeds in this sort of situation, we've got a GeoGebra file which we can just investigate what goes on for different values of E and different angles of approach. So this is the file then, and you can see I can vary the values of the initial speed and angle, so in effect the initial velocity, and then look at different values of E. So let's just see what happens in this case, where we've got an initial speed of 4 at an angle of 30 degrees. So there we are. We can see then that afterwards we get a speed of impact of 2.65 when that angle there was 60 degrees. And you can see that the angle of the object coming off here is at 40.9 degrees afterwards. I can vary the initial speed, so if I just reset that, let's see what happens if we have something which is going a little bit slower this time, but at the same angle and same coefficient of restitution. And you can see again that we've got this 40.9 degrees coming off there, but of course the speed afterwards is going to be slightly different. So let's leave that on the screen and just alter some of these values and see what happens. So first of all, let's alter the value of E and reducing it. And you can see there as I reduce it then that the angle is increased there, and with greater values of E we get to a point where in fact the angles there, when E is equal to 1, so we've got perfectly elastic, the angles are equal to each other at the so it's hitting the wall at the same angle as it's rebounding. I can just check that by changing the angles, and you can see there where E is equal to 1 the angle is always the same for the approach and then rebound. Reducing that, and you can see that the rebound angle reduces, so reducing E changes the rebound angle to being rather less. Well, this is the example I'm going to look at now to see if we can actually calculate the values and see where they come from. So let's just run this. Now you can see then that the speed of impact, so the speed after impact is 2.65 and that the angle there is 40.9 degrees. Right, let's look at the mathematics behind that to see where these numbers have come from. So this is the situation that we're looking at then, where I have the initial speed of 4 meters per second and the angle of approach to the wall is at 60 degrees. So on there I need to now consider this as being as two separate motions, one which is perpendicular to the wall and one which is parallel to the wall. So if I let the parallel one be U1 and the perpendicular one be U2, then the first thing, going parallel to the wall, we know that the speed isn't going to change, so that the initial value U1, which I can get by looking at the components of the 4, that's going to be 4 cosine of 60 degrees, and that of course cosine of 60 degrees is half, so therefore that is equal to a value of 2. And that's not going to change, so if we look at the final velocity, the velocity after impact in terms of its components, if I call this one here the V1, then I know that V1 will be equal to U1, so that is equal to 2 also. But now considering the perpendicular motion, the rebound, which I'll call V2, divided by U2, the initial one, so we have V2 over U2, that will be equal to the value of E, coefficient of restitution. But looking at the perpendicular components, U2 is going to be equal to 4 sine 60 degrees, and that's equal to 2 root 3. Sine 60 is root 3 over 2, so 4 multiplied by that is 2 root 3. And we know that V2 is going to be E multiplied by that, so V2 is E multiplied by U2, so that's 0.5 multiplied by 2 root 3, so that's equal to root 3. So the velocity then, if I take my component directions the usual way, I and j, then the velocity afterwards, v, is going to be equal to negative root 3, so it's negative v2 in the I direction, plus 2 in the j direction. Now we're asked to find then the speed, so the speed is just the magnitude of that, and that will be equal to the square root of root 3 squared plus 2 squared, so that's going to be in total root 7, or 2.65 meters per second. To find the angle that is coming off the wall, then we can use the components here, say that this angle theta, so to the perpendicular, that's going to be tan to the minus 1 of v1 over v2. So theta is tan to the minus 1 of 2 over root 3, and that comes out to be 49.1 degrees. And so the angle to the wall is 40.1 degrees, which was, if you remember, what we had from the GeoGebra file. Well, that's the end of this video, and indeed the end of the section on impulse and momentum.